When talking about regression, we need to talk about the difference between population regression and sample regression. So if we talk about population regression line first, it's the relationship which holds between x and y if you consider the whole population. Okay, so we write the population linear regression model as the y for each instance equals the true value of the intercept and the true value of the slope. And you notice that these betas, they do not have the hat on top. Okay, it's because these are not estimates, these are the true values. Okay, and what we have is that we have the y, we have the x, and then we have the true population line. It's a straight line. Okay. And we have this because we are considering the whole population, and maybe this is a relationship between the education level and the salary of the people of a whole country, for example. So here you have maybe millions of data points, and then you can fit a line through all these data points. Okay, so you see, or you look at the average years or the years of education towards the salary. So this beta naught is the intercept, the beta 1 is the slope, and the slope, it tells you for one change or 1 unit change in the x, in the years of education, how much would you expect y to change. Okay, or a given level of x, what level or average of y would you expect the salary to be. Okay, and it's important to realize that these coefficients, the intercept and the slope, they are constants. They do not change. Okay, because here you have consider the whole population and nothing but the population, so these are fixed. Okay, and these betas, when they are not with the hat, they are the true values. Okay, and conversely, or it's important to know that the error term. Okay, so we often call this the error term. So and this error term in the linear equation contains all factors affecting the y variable, which is not accounted for by the x variable or the x variables that we have included in our model. So when we collect data from the population, because often we do not have the data for the whole population, we have to take a small sample because it's unfeasible to get data for the whole population, or it's just too expensive. We can take a sample, okay, to get an estimate of the parameters. So we get some sample regression line. Okay, So what we do is that we just gather some data on X and Y, and instead of having millions of data, we have maybe a couple of hundred data, because that's what we need for our study, or that's what we can afford. And then we can fit this sample regression line. It's just the equation of a straight line, and we can try to fit the equation line here, okay? And then we would have the beta naught hat, and the slope would be beta 1 hat. And these hats, they indicate that these are not fixed entities. These are not constant. They are just estimates, which means that if you redid this experiment, okay, or this analysis, not experiment, if you redid this analysis, then you would most probably get different values for the intercept and the slope, because you would get a different data set, okay? So these beta hats, they are actually varying depending on which sample you are looking at, okay? And we can use that at a later time to estimate the probabilities of the values of these parameters, or these coefficients. So, some important features to note about the sample regression line is that the hat over the y, so the y hat indicates that it's a fitted value, okay? So this is our prediction. It's our best prediction. And what this is, based on the ordinary least squares method, is we find the the best fit line on average, okay? So we can apply the formula intercept plus the slope times x to obtain a predicted value of y hat on average, okay? So this is quite important. On the next slide, I will mention why. Where beta naught hat is the intercept, and beta 1 hat is the slope of the sample regression line, okay? And not all points lie on this line, so we get some deviation, okay? And this deviation we call a residual, and we denote that uy hat for each data point. So for example, we have a fitted line, x and y here, and we have some data here, and this uy is just the difference between the y I and the y hat I, okay? So the residual is just the difference between the actual value and the fitted value, okay? And so you see that since it's a difference between two y values, these residuals have the same denomination or units as the y variable. So in our example, for example, our salary is measured in euros, then you have the actual data points value in euros, you have the fitted value in euros, and the difference between them is measured in euros. Okay, so this, in our example here, we have a positive residual because we have yi minus y hat I, which is positive because yi is, or our data point is above the fitted line. For this data point, the residual would be negative because the data point is below the fitted line. Okay, so how do we choose the intercept and the slope? Okay, how do we choose our coefficients? Well, what we do is that we minimize the sum of squared residuals. Okay, so remember that the residuals, I will have to skew my pad here a bit. So we have some residuals, and we look at the residuals here, and we square them. Okay, so we square them. Sum of squared residuals. Okay, we get that, and this is often shortened as SSR. And what we do is that we just take the square of these residuals, or 1 u2 squared and u3 squared, and for example, we square them, and what's important is that even though we have a negative residual, it's coming out positive, right? Because any number you square becomes non-negative. Okay, so you try to minimize these squared distances between the data and the fitted line, and that would be the square of this difference, and the fitted line. Okay, the fitted line is just this intercept and the slope times the x, right? So now you have this equation for the residual, and you square it, and you take the minimum of that. How do you choose that? Well, you take the minimum by changing the parameter, the intercept, and the slope. Okay, so under the min, you often put the parameters you can change to minimize the expression. So you find the intercept and the slope, which minimizes the sum of squared residuals. Okay, so often students wonder why do you square the residuals? Okay, why are they squared and not just residuals? Okay, well, that's because if you only use the residuals, then you would not get an equation which gives you the average, the expected average of y given a certain value of x. For example, if you take the absolute value of the residual, then you could minimize the sum of absolute residuals. You would not get the expected average y given a certain value of x. You would get the median of y, or expected median of y given a certain x. So that would be an example of robust regression, which we are not looking into here, but in case you need to get some robust estimates where you need the median of y, then you know what to do. You can run a robust regression, and this regression minimizes the absolute value of the residuals. But the ordinary least squares minimizes the squared residuals, because then we get the average or expected average of the y variable, which we often or most often are looking for. So based on this on this formula for minimizing the minimum or the sum of squared regression or residuals, we get some important formulas. Okay, so for example, we get a formula for the slope, which is beta 1 hat, the estimated slope, which is the covariance, the SXY is the sample covariance of between x and y. So it would be the same in our education salary example. It would be the sample covariance between the number of years of education and the salary measured in euros. And the SX squared is the sample variance of the x variable. In our example, it would be the sample variance of the number of years of education. So, and so given only one explanatory variable, 1x, then you would easily find the slope by applying this formula. And the estimated intercept you can calculate that by using the information from the slope and adding or applying the average value, the sample mean of y and the sample mean of x. Okay, so and if you want to look for a complete derivation of these expressions, then you can look at the appendix 4.2 of Stock and Watson. Okay, but there are some important properties of this regression line, and one is that the line always passes through the point average x and average y. Okay, sample average x and sample average y. And you see that by arranging the equation for the estimated intercept, and put the average of y, the sample average of y on one side and the rest on the other side, and you see that this sample regression line goes through, which is y hat, y goes through the sample average of both x and y. Okay. In addition, you have that the sum of the residuals equals to 0. And the reason why we can say that is that we include this intercept in the equation, and this intercept makes sure that our sum of residuals is 0. Okay, if we did not have this intercept, that assumption or property would not necessarily be true. Okay, and next we have that the product of the or the sum of the product of the residual and the x variable, it's equal to 0. So the sample covariance between the ordinary least square residuals and the regressors, it should be 0. Okay. So that's it for this video, and see you next time.